Hello and welcome to the next chapter in our VELOVirtual webinar series. We're going to give a couple minutes for folks to join here, but I do want to kind of kick things off. I'm excited to be here today to talk about how AM can fast track your supply chain. Today, we're shifting gears a little bit. Rather than diving into a technology or an application like we normally do, we wanted to walk you through the power of additive manufacturing to radically restructure and rebuild the supply chains for your critical parts. Obviously, this has been a promise of AM for a while with faster R&D, scalable production, on-demand digital inventories. You've heard all of that before. But for a lot of parts, AM struggled to deliver that on that promise. And there are really three reasons why, which we're going to dive into here today. First, it can take a long time to get the first print right. It can take months of PhD level development in some cases to get the first part off the printer doing what you want it to do. And then once you get it right, how do you keep it right? Quarter to quarter, system to system, and site to site. A lot of these printers operate independently from the rest of the fleet, and they can have individual fingerprints. So kind of this prototyping legacy of conventional additive manufacturing has leaked into this production mindset, made it really challenging for folks to go into full-scale production. The third reason, post-processing. So the post-processing needed for conventional AM solutions can be really difficult and often leads to frustration. Just because it looks like an impeller doesn't mean that it's going to balance or spin like one. And we've seen plenty of trade show parts that when you go into testing, don't pan out. So the good news is that all changes with VELO3D's support for on-demand printing. By leveraging contract manufacturing partners like Duncan Machine Products, who's here with us today, you can now access VELO3D capabilities without the need to purchase a machine. So think about that. This means that the movement to AM no longer has to be strategic. This is no longer a multi-million-dollar initiative for your company. By contacting partners like Duncan, you can manufacture the part the same way you would using traditional manufacturing. And now the move to AM has never been easier. Now, let me introduce our speakers. Joining us today is Aaron Miller. He is an additive manufacturing engineer for Duncan Machine Products. Before joining in 2020, he worked as a design engineer for Halliburton Energy Services. He holds a Bachelor of Science in Mechanical Engineering from West Texas A&M University. And we also have Zach Walton with us today. He is the Director of Energy and Turbomachinery Applications at VELO3D. Before joining VELO3D, Zach worked multiple positions at Halliburton Energy Services, ranging from R&D engineer to product manager. He holds a BS and MS in mechanical engineering from Texas A&M and has over 70 granted patents. Wow, fantastic work, Zach. And Zach, I will turn it over to you.
Yep, thank you, Mike, and thanks everybody for joining. So our goal, kind of like Mike said with this webinar, is to really walk through additive manufacturing, how it can affect supply chains, and really what our technology here at VELO3D has opened up even further. And doing that, channeling it through a live demonstration through Aaron Miller at Duncan Machine Products, and leveraging kind of like what Mike said, using ourselves who are traditional design engineers and have started our journey on additive manufacturing, but did not have to be process development or traditional additive engineers to be able to leverage metal 3D printing. So first, I wanted to jump into the drivers for adopting additive manufacturing. And so oftentimes people talk about the next generation development projects. So projects that are basically like a white slate. There's no precedence, and you can include additive manufacturing as one of the manufacturing processes, knowing that you're going to go through the testing, validation, everything on the onset, and there is no background historic information to vet it against or through. But what's often missed, and was one of the promises of Metal AM, was to help with standard development projects as well as spare parts. So starting off with standard development projects, these are projects like what me and Aaron would have worked on in a previous life that is gated by a lead time, milestones, and the goal is to get it to market and monetize that upfront work. Often because of standard manufacturing processes, your timeline starts stretching out, your need to get to market is a little bit quicker, and you either lose out on the ability to optimize, or it's a longer stretch to try to get something in the market. So additive promises to be able to help out with that, as long as it can be a very rapid and fast response. The second part of, for spare part replacement, which is linked to standard development projects in a way, is the aging infrastructure of industries today, end users and OEMs trying to replace parts that are currently in a warehouse or needing to be replaced that are no longer in service and don't have a structured supply chain. So fixing that need now, but also looking into the future and making sure that that critical mass of parts being stored and being replaced is not having to be realized again by having this ability to have a digital file as a spare part for a standard development project. So basically coupling those together, fixing the problem now and in the future. And so why is this important now? So I think like most people are starting to see, the lights are starting to flicker a little bit, and you know, we're starting to come out of the kind of what everybody experienced in 2020, but there are still aftershocks. So massive layoffs and restructurings have completely eliminated, you know, centuries of experience in the standard manufacturing processes. Idle equipment from OEMs and users now will need to be refurbished, replaced, or new equipment coming online might require replacement in the near term. And so all these effects will continue. We're feeling them now, but they will continue to shape and evolve all the different industrial markets. So continuing into a real quick overview of 3D printing and really how it stacks up in our experience from casting, machining, which are some of the standard processes. We've created this graph on the bottom left, or the scale, where just giving a scale from worst, average, and best. And if you take tolerancing, for instance, you know, starting with castings, it has a fairly wide open tolerance. And in machining, which is kind of the other end of the spectrum, has a very, very tight tolerance. Additive falls somewhere in between. It'll be a better tolerance than casting, and approaching, but not quite to what some of the machining, especially if you're machining two components and welding them together, might be able to achieve. You know, transitioning to surface finish, again, starting with machining, you are going to get a machined surface finish once that process is complete. And what you're looking at for casting and additive is once the process is complete, is you know, a very comparable surface finish. But where additive really shines is now focusing into the lead time. So the ability to have the print, which can be a matter of days, or the process to manufacture be a matter of days with no upfront investment on costing and extensive planning, you're able to produce a part or have the manufacturing side of the process complete in a matter of days. This allows times for surface finish refinement, for other processes that might be required, if applicable, to really turn that 2 closer to a 3 on the surface finish side for additive. Whereas with castings, after you've gone through the upfront investment, the time, and now finally have the casting, you're already several weeks to months ahead of where additive would be in terms of lead time. And so you don't necessarily have that opportunity to invest. And so you see at the bottom, we kind of call it that 3 to 4 weeks. That's really including, you know, not just the printing, which is on a matter of days, but the thermal treatments, the machining, and any surface finish refinements, like Aaron will cover on his section. So what is laser powder bed fusion? You know, kind of in a nutshell and at a high level, it is taking a part and slicing it into individual layers. For us here at VELO, it's 50 microns. And as you can see on the left, now that I've lazed that layer, the piston will drop 50 microns. It will lay a layer of powder, an even coated layer of powder, and then it will laze that next layer, and then continue down that process until you basically micro welded a fully dense part out of the printer. The next section is really on why supports are needed. This is a typical topic and kind of one of those first barriers that you can encounter when you start developing or wanting to develop additive manufacturing. On the left, you see the desired outcome. So this is what we would kind of coin an overhang. And let's say this is what the legacy part is, and this is exactly what you want to be able to print. But if you were to print it on conventional AM, due to the internal stresses you see without supports, it's going to buckle and basically peel up. And so supports have to be added and are essentially anchors, preventing that destruction during the build, as well as not just destroying the part, but potentially that equipment. And so taking that into context for the first difference in conventional printing, and really the scope of this webinar, channeling that through a part that's a very good use case for additive, and especially a very good use case for VELO, is a shrouded impeller. So on the left, you see conventional option number 1, printing the part as is. So flat on the build plate, which is ideal, but all those all those unsupported areas, you do have to fill in with stick supports or some amount of support structure. And you can imagine metal being welded to metal in that fashion, removing that material, getting to where you could process the internals. Before you know it, you're basically right at where casting would have offered in terms of lead time and difficulties. One option that's been considered or been done in the past is rather than changing the design, maybe change the build orientation. If I can tilt it at 45 degrees, I should be able to get rid of supports. 2 things happen there based on experience: is the build gets taller, which makes the build more expensive, as well as your GD&T, or the ability to print a round part, starts becoming a challenge and can lead to issues with balancing or spin testing a part, you know, similar to a shrouded impeller. So rather than having to deal with any of those complications, the ability to print support free, like you see on the right here for the shrouded impeller, given the well-constrained geometry of a shrouded impeller, you can see what we're able to do on the VELO AM solution, being able to print these internal areas without supports at all. So going into like the overall manufacturing workflow, you can see on the top left, it's typical to any of the manufacturing processes. I have a part that I want to make. I have an engineering drawing with it, and this is the final configuration that I want to receive. The next step in terms of printing is no different than something like casting, where you would have an as printed configuration. So in this instance, you can see the constraint wall that we showed previously attached in CAD or drawn in CAD to the outside of the impeller, as well as any type of machining stock that might be required. And then that file is put into print preparation software. So print preparation software will slice the part and basically give the locked instructions in a print file so that the printer can actually print the part. Once the part is printed, after that is where the post-processing begins. Like we discussed, in a matter of days, the part is complete. It's welded to a build plate. It goes through some amount of stress relief that will allow the part to be cut off the build plate without any adverse effects to the dimensionality of the part. And then from there, it's going from that to a finished part. There's thermal treatments, machining, and any type of surface finishing that might be required. So how does VELO basically lower the barriers that we're traditionally seeing in that workflow? Previously, we talked about the limited need for supports, which is one of the aspects. The other is the ability to have our flow preparation software be able to apply a unique processing condition based on what it sees in the geometry. So rather than working with an STL, it's working with the native CAD file. And as you can see here, it knows bulk core, low overhang, vertical walls, and it's able to prescribe the correct process. So what that's done is allowed folks like myself and Aaron, who are traditionally design engineers, to focus on the design intent and allow the flow print preparation software to be able to prescribe the correct process set to create the print file and ultimately be able to print the part. And so here's a screen capture in our flow preprint software showing basically moving up in Z like you would be printing the part. For the build that we're going to discuss, and Aaron is going to walk us through, but showing basically the native CAD file in our flow print preparation software and building up in Z. The next part is, so now that you're through the understanding and the kind of qualification and understood in terms of your design and tolerancing and surface finishing, you're well on your way to be able to produce a part, whether it's a proof of concept or a prototype. The next limitation was, how do you take that now into full production? Most people don't want to go through a new manufacturing process if they don't intend to produce it on a larger scale. So one of the big needs that was out there was really on the quality side. And so this is where the VELO Assure quality software comes into play. And so starting on the left, you can see the pre-built system calibration is one of the unique features of our Assure software, where understanding the machine health of the ability to understand before you actually run your print on any single build is extremely valuable and able to be done through the Assure software. It's also able to calibrate with a one-click button. So everything is basically contained in the printer and you know your machine is healthy before every single print. This also allows for an independence to print serial number, which we'll cover here in a second. The next step is really all the data that's being collected and what's happening during the print to be able to have access to that information. So build tracking, basically validating and tracking the critical parameters and making sure they stay within a control limit, as well as height mapping to understand the quality of the powder bed and any type of part protrusion. So how the part is performing every single layer, so during the entire build. And then taking all of this information in an auto-generated report that's available with every part that's printed on the VELO system, which is really the first push into a quality type document used for the different quality standards, things that are out there for all the pertinent information you would want to see in a very easy digestible document. So defect detection is extremely applicable here, but is another new feature. So again, in the same realm of taking that data and doing something useful and digestible with it. So in this sense, it's enabling real-time detection of surface defectivity. So you can see on the left, on the low angle areas that are printed without supports, you can see on this left section, this particular print had some surface defects. And we were able to see those through the software rather than waiting till the end of the manufacturing process. So getting through machining, surface treatment, and getting all the way a week or so down the line to then realize you could potentially have a problem or a potential deviation in the manufacturing process. The ability to see it upfront and either see if there needs to be a deviation, or on the right, knowing it's a good part. Seeing that right when the part comes out of the printer is extremely valuable in the matter of time and trying to secure a faster supply chain. And the final step is really on the enterprise-wide scalability. So we touched on this because of the way our system handles calibrations and the way our flow print software works in unison. We don't have that calibration information embedded into the build file like you see on some of the incumbent systems. And so at the top, you can see why there's been an issue of folks using this technology to span globally, printing it at kind of having that open network across the globe, or even just printer to printer. You can kind of see how that build file spans out and nothing's ever locked into that digital format. And on the bottom, you see how it would be handled in our system. Once a build file is created, it's able to print on any VELO system anywhere in the world, as long as that system is in calibration. So meaning you run through that one-click checklist at the beginning, everything is green, and you know you have a healthy printer, that build file will print the same on any of the systems. And so now I'm going to hand it over to Aaron, who is going to go through the full workflow in real life.
Thank you, Zach. So before we go through the real world demonstration of this process, making these parts, just a quick background on DMP. We started in 2007 by our owners in their garage with a couple of machines, and we've expanded drastically since then. We're up to about 60 employees. We started off machining oil field parts, and we still do, but we've also branched out into aerospace. And then last year, we added metal AM to our capabilities. We started off with that printer on the right, which is Inconel 718. And then we added TIE 64 and aluminum F357 there on the left. And we're about to get a Hastelloy machine next week. So that little background out of the way. Let's go ahead. So just like Zach had outlined earlier, we get the CAD model from the customer, we make an as printed model and add any machine stock that's necessary, drag and drop into the flow preprint software, slice, that goes to the machine, and then we get parts out, cut them off the build plate, do any post-processing that's necessary, and machine to print. So just a close-up view of the as printed model. Like Zach said, there's no support structures that are necessary to be put inside of the vanes. Generally, all we do is revolve a support wall around the part, or a constraint wall, and then we add some stock on the bottom to give us room to cut off with an EDM. So this is just this is basically all I do in Flow. It's a little boring because VELO's pretty much got it streamlined and figured out for us. This just lets me drag and drop, hit slice. I don't have to worry about parameter studies or anything else. And I can focus on the post-processing and all the other steps that follow after it comes out of the machine. So here's a shot of it printing. You can see the argon carrying off the soot and to the right there. The current machine that VELO has is big enough to print a 300 millimeter or about a 12-inch diameter impeller. So after everything is done printing, the machine's full of powder, and they have to vacuum out all the powder and recycle it into the system. So with VELO system, the powder never touches oxygen. It's recycled into a hopper and sifted to a sieve. Here's us unloading the plate out of the machine with our lifting device. And there's the as printed parts welded to the build plate there on the right. So now that we've got it out of the machine, it's time to do post-processing. So something that has been pretty common over the past few decades in metal AM is hot isostatic pressing. And this is just putting the parts in a very hot, very high pressure argon atmosphere. This is maybe about half our customers do this. It depends on what your needs are and what your requirements are. So another thing that we can do is go heat treat these parts after they come out of the machine. So in the case of Inconel 718, it's a solution and age process, and that table on the right there is from VELO's material sheet, which they provide, comparing the as printed properties to the solution and age properties. So after those come back from any thermal processing required, we take them and put them in our EDM and cut them off the build plate. And that on the left there is in the lower half is a little stainless catch basket to catch the parts once they come off the plate, so they don't drop too far distance in the tank there. And then on the right, there's 2 impellers cut off the plate, ready for the next step, which is machining. We turn that constraint wall off the OD. We can face, we can do any other machining operations that are necessary to get the part to print. And another thing that we can do is use what's known as vapor blasting. This process is more gentle than like sand blasting or bead blasting, and it'll remove any oxide layer, and it'll improve on Inconel. We've seen it improve anywhere between 50 to 100 microinches, depending on the angle of the surface that you're blasting. Let's see. Another thing that we can do is abrasive flow machining. So this process is basically just taking a media. It's kind of like silly putty with sand in it, and we flow through the inside of the impeller at pressure to polish the inside surfaces. Not everybody needs this, but it's a pretty fast process for impellers. The fixture you see is 2 parts that clamp together over the part, and we generally make like a main body, and then we can 3D print an insert that goes in there that conforms to the top shape of the top shroud. That takes like a day. So if we've done, a 6-inch or 12-inch impeller before, we can generally have a fixture ready in a few days. And the little black plug at the bottom is to plug the ID to make sure the media is channeled through the veins. So the results of this process, you can get a very nice surface finish like you see on the left, just depending on what your requirements are. And the real cool shot is on the right there. That's after just a few passes with extrude hone through this impeller. You can go from, as printed to a really nice surface finish very quickly. So yeah, this is the final result. I've got that right here. So this guy came out of the printer exactly 4 weeks ago today. This has had everything done that you've seen in the presentation. It's been hipped, it's been heat treated, it's been EDM'd, machined, vapor blasted, and AFM'd. And yeah, I mean, this isn't the most complicated impeller, but if you understand the manufacturing process of AM, and you understand limitations and capabilities, and you know what you want, I mean, 3 to 4 weeks is definitely in the ballpark. So with all that said, I'm gonna go ahead and hand it back to Zach.
Yep, thanks, Aaron. So kind of progressing forward and kind of wrapping up the last 2 sections of the webinar is really, how is all this accomplished again at a high level? Really what we focused on here at VELO is lowering these barriers, and what you see here are the 3 steps that are involved, or the 3 items that are involved in the VELO manufacturing process. So starting with the flow print preparation software, as you heard me and Aaron describe, that lowers the barrier, eliminates the need for necessary process development, and allows the next generation and the current generation of design engineers to really be able to implement additive and really focus more on the design intent, the surface finishing, the tolerancing, and getting very quickly, on a matter of a day, if not quicker, from a CAD to an as printed model, and then into the print software for instructions. And then the Sapphire printer itself, which is able to print, in this case, this impeller build was about a day and a half. Having the hardware such as the non-contact recoder, as well as the expanded sensing and metrology capabilities to make sure that the process is performing correctly, and being able to perform coming from the flow instructions. And then all of that data being used, as well as the calibration information in our assured quality validation software, which is critical in moving things from prototype into production. And all of this has enabled, like you saw in the previous section from Aaron, being able to focus on the post-processing elements, and then as demand increases and things can scale accordingly, just all over time being able to increase the speed based on these pieces all being kind of done in this ecosystem of the VELO manufacturing process. The final sections are kind of based on some of the traditional questions we get. The first one being on material properties. So what we've traditionally seen is mechanical properties are better than casting and starting to approach the forged metals. In terms of density, our internal spec for most of our alloys is a relative density of 99.9% out of the printer. And then in geometric accuracy, the rule of thumb is for kind of small dimensions, the plus or minus 50 microns. And for some of the bigger dimensions, a good rule of thumb is at that plus or minus 0.2% of that dimension. The next part is if the size, making sure that the size actually fits what can be printed. So like Aaron talked about earlier, the current sapphire that prints today is at 315 millimeters in diameter and 400 millimeters tall. It operates with two 1 kilowatt lasers, and the Sapphire MZ is the same architecture. It's just the elevator has been re-engineered to go to a full 1 meter build height. But what we are started to develop and will start deliveries at the end of this year and into 2022 is a Sapphire XC. And so this is important for multiple reasons. One of which is you can see the build volume of the standard Sapphire inside the XC. So for X amount of parts that you can fit on there, you can fit much more on the larger build volume. It also operates with 8 1 kilowatt lasers instead of 2 for a dramatic increase in throughput and really that next step of production. And where we traditionally see is now starting to approach some of the lower run casting costs. The other feature that it brings to the table is the ability to print larger parts that traditionally weren't able to be printed or manufactured using laser powder bed fusion in the past. So with those kind of, now that the size is there, understanding the cost as well. So again, kind of normalizing the cost on the left in terms of what is printed today on the Sapphire. What's being completed right now and out in the field is upgrades to our recoder system, as well as our process to basically gain some efficiencies and have that continual improvement that you see with the abilities that we've been able to bring to laser powder bed fusion. And what we see is around a 30% reduction, really depending on what geometry of part it is. And then the big hit on cost coming with the Sapphire XC, like we discussed, the drastic increase in throughput and lowering of cost, where we're seeing upwards of 75% reduction depending on the part. Really gaining to that next level of production and unlocking that next level of parts that can now make sense on additive manufacturing. And so, people starting with the Sapphire, working with the Sapphire, and building their supply chains ready for when Sapphire XC is fully commissioned. Those are the activities currently going on, and then just realizing that cost reduction and increase in part count as kind of that next step in their supply chain evolution. Just for a graphic, so again, today what was printed over the last 3 to 4 weeks, like Aaron mentioned, is the Sapphire today, the 2 impellers that he walked through, and you can see those on the current build plate. And then on the right, just for graphical representation, is the same size impeller, being able to fit 9 of them on the XC once it's available. And you can kind of picture also being able to build just one large impeller as well, which previously was not able to be manufactured. So in summary, a lot of what's driving this webinar, these discussions, things that we see in the market are really the effects of 2020 continuing. It seems like the different industries in the world are starting to kind of come back to life, but we will always be dealing with the shaping and evolution of these industrial markets because of the last year to year and a half. And with that comes the need to look at technologies or approach technologies that people might have wanted to approach but found certain barriers to it. And with the VELO 3D manufacturing process, we've shown, hopefully through this webinar, that we've eliminated some of those steps that allows everyday designers, allows more of the development projects and spare part type projects to really be considered seriously, and then scaling accordingly as the XC becomes available, and as OEMs and users start becoming more comfortable with additive manufacturing as a process.
Thanks, Aaron. Thanks, Zach. Great job today. We do have a number of questions coming in. So, once again, if you have a question for the panelists, Aaron or Zach, or I guess even me, submit them through the Q&A channel, not the chat channel. I've got the Q&A window open here. I'll be monitoring that. And I do want to start off one. Do you need a separate machine for each material? So we'll start there.
Yep. So the way the Sapphire is configured, we've kept production in mind. So if you're in a production setting, absolutely, each machine would correspond to an individual material. We do have people that have looked at, keeping it within the family like a super nickel alloy, but we don't recommend that in a production setting. We recommend getting the system kind of up and running with the demand there, and kind of just printing with that standard alloy.
And I guess for Aaron, you mentioned the alloys that you have on site. It sounded like you have like almost one of everything.
Yeah, I mean, we've got Inconel tie, aluminum, and like I said, about to get Hastelloy C22. On that previous question, I mean, it's possible to swap powders, but like Zach said, it's better. You don't want to cross the streams. You want to keep the powder pure in there.
And I'd say, if you're interested in a part, and if you just want one point of contact, having DMP as your point of contact gives you access to all the metals. So you don't have to worry about swapping powders at all in that case, right? Here's one. We always get this one, but how does the machine handle the warpage of the part if there aren't any supports? Or how do you print support free is another way to say that one.
So at a high level, there's kind of two parts to that. One is there is a little bit of raising in the build and a little bit of warpage that is allowed, and it's actually a very stable process. And so a tighter control on the process in general, coupled with the ability to have a non-contact recoder and be able to allow for a little bit of that is really, at a very high level, what allows us to do those type of things.
Okay. And what's the thinnest metal thickness we can print?
So it can vary sometimes between materials, but for like completely leak tight in terms of like a heat exchanger, you're in the kind of 250, 300 microns for like a vertical wall, and then that will go down as the angle goes down. We've printed much smaller than that. And when I say it's not like heat exchanger leak tight, I don't mean it's Swiss cheese. It just not the 99.9% density. It's more in the 99.5 or 0.5, let's say. But for those, we've been able to see down to 150 microns, not a little bit smaller for certain alloys. And as long as they're also constrained correctly, right? If you print it, too far up and there's no constraining, you can worry about a part, kind of buckling a little bit.
There was somebody who wanted a little bit more explanation on the unique processing conditions and how the system works with flow to print the parts accurately.
In terms of, so the way, kind of flow in general works is we've worked to kind of generalize part families. And as we see more challenging parts to our process, being able to bring that in-house and making sure it can be generalized in flow. The ability to work with native CAD allows us to, use the geometry and focus on the software understanding, that this is a lattice or a vertical wall or a thin wall, angle wall, as well as some process overrides. So, Aaron or myself, for example, can select a internal hole that we might want, or an internal channel that's very small that we might want the best surface finish. And so we can actually select that surface and apply something like one of our overrides called miniature, which is basically telling the printer, I'm okay with a little bit of increased cost, but I want that surface finish to be as good as laser powder bed fusion can get. Answers the question, but that's probably all we'd be able to go through.
Kind of last one on the process, but what is the non-contact recoder? I think you referred to that earlier.
So basically what that means is we have a way that we drop a little bit more of excess powder. And then what we have kind of a bulk wiping to get rid of the top layer of powder. We don't actually contact the, that 50 microns that you're going to be lasing on. We have a proprietary way that we don't actually contact that surface and still get the same quality of the powder bed.
Aaron, one for you. How long did it take you to, they use the term write the objects in your presentation? I think this means like kind of import and prepare and flow.
Maybe an hour, including slice time. Like I said, I just drag, drop, hit slice. There was no extra parameters for me to worry about messing with.
A couple questions on post-processing. What non-destructive methods would you use to find porosity or look at under the surface defects?
So, I mean, you can do several things. You could either print a witness coupon with the part if you're concerned about that, just print it at the same time with the same layers. You can also, there's X-ray, there's CT, there's, those are the big ones I can think of. The coupons are the easiest thing to do.
One here on CNC machining. Can you comment on the process of setting up the part for CNC machining? Do you include any steps to account for slight differences in part geometry?
Sure. I mean, so we add stock generally to any surface that has a very tight tolerance, like 1 thou, or anything that has a very tight surface finish requirement, so that we can go in and machine it. We just add extra material all the way around the part. But I mean, at the same time, we do leave a lot of surfaces as printed. It just depends on what your requirements are.
I think that loops into really the CAD side of it too. I think kind of one of your comments, Aaron, was about an hour to work in flow, depending on how, how much stock needs to be added or how the native CAD is received from a customer. Sometimes that can take the longer time is just setting up the CAD for what needs to be machined afterwards, creating that as printed model.
Right. And there's a question in here about dealing with the CAD is, do we convert it to STAP, or, is there, what kind of file formats do we use?
Flow works with native CAD. And that's something we do run into sometimes. I think folks are traditionally used to sending an STL. So we don't, our software doesn't work with an STL at this time. And the reason for that is we need the fidelity in the CAD file. So we traditionally work with that step file and work with the customer, especially on Aaron's side, of helping them get to an as printed CAD model. Because from our days working in bill of materials, right, you're eventually going to have a finished part, and then in that bill of material, you'll have an as printed, like you would traditionally have an as cast model. And so providing guidance, working towards getting to that being a kind of standard process forward is one part of it. The second part is the native CAD file, traditionally a step file, is what's required.
One for Aaron. Does DMP do any balancing on the impellers? Where would that normally be done?
So we currently do not have that capability. I mean, we're certainly open to adding that to our list of things that we can do. We've actually started looking at that. So if anyone's interested in talking to that, hit us up.
Zach, there were a couple questions about Assure regarding how does Assure work, and then specifically defect detection.
So details of defect detection, there is, I think it's webinar number 12 that goes into the more intricate details. I won't be able to kind of talk through that on this webinar, but Assure in general, there's multiple steps of it. One is kind of a factory floor setting. So somebody like Aaron, who has now is going to have 4 printers, he's able to have a dashboard, see all 4 printers, see what's printing, when it's printing, what's happening, get alerts if there are issues that pop up or outside of one of the limits that's being tracked, or an interruption or what have you. And then during the print of each one, we are collecting the data that we discussed a little bit before in terms of oxygen, humidity, the peak height from the height mapping image, basically tracking that over time and making sure it's within an allowable limit. If it's not, it'll send a warning to Aaron. And if it gets completely out of it, where it might have damage to the printer, like a part raising too much in the bed because a support wasn't added correctly, let's say on the bottom, then it'll basically stop the print. And so all that information is digested along with the build data, the time it started, time it ended, powder usage. A lot of the information that a lot of the standards and specifications nowadays are really kind of lining out that they want to see, plus more is basically auto-generated to where after the print's done, Aaron on his systems or myself at our headquarters can go click a button and have that 2 to 4 page PDF with all the available information, including the calibration information. When was it last run? What were the values, and making sure that the machine was healthy before that print was run.
There's a question here about, can we vary the laser spot diameter for better productivity? I think you referenced this to sort of process overrides, so maybe it's better to answer it with the process overrides side.
Yeah, so when you think of like parameter development or things along those lines, the process overrides, that some of that stuff is what it's doing. It's at a macro generalized level, changing some of the parameters, whether it's like what you're saying, laser power, laser spot size, to be able to do different things, but really focusing from an engineering standpoint on the features themselves, or the surface finishing, things like that.
This one's kind of interesting. Can closed shrouded impellers be printed without internal supports?
What was the question?
Can you print a shrouded impeller without internal supports? I think they just want to confirm that what we're saying, that we can do it. Yeah.
And kind of going back in slides, if I'm able to here.
Oh, there it is. Aaron's got it.
Yeah. And this image right here, this is after the OD has been turned. So going, there's nothing intricate done with the powder or done with, anything else. It's standard laser powder bed fusion. But once the part comes off, once the part comes off the printer and that outer wall is turned off, this is the interior as printed surface. And then straight into something like abrasive flow machining or vapor blasting or other surface finishing processes.
Yeah, you can really see, and that internal channel, just to be really clear and kind of repeating it, there are no internal supports when that's printed.
Yep.
Yeah. There's some questions about tolerance, and maybe going back to the tolerance slide would help close those out. Maybe talk through what we're able to print. You mentioned two things for small parts and big parts.
Yep. Yeah. So in terms of a shroud impeller, what we really mean by tolerancing is if you take like the distance between the top shroud, bottom shroud, if you were to CNC machine that or braze and weld it, if you wanted to, you could spec something very, very close to like plus or minus a half thou or a thou. Not that you might need that, but it is doable. Right out of the printer, using flow, you're not going to be at that tight of tolerance. We give this kind of generic plus or minus 0.2% for kind of larger diameters, and then plus or minus 50 microns when you're talking about like very thin vertical walls, or something that falls into the those very tiny features. But that's kind of what we mean on the shroud impeller side of it. This is a rule of thumb. Printing that part, that distance is something we see in terms of having a little bit of more of an open tolerance compared to machining, but a much better tolerance than castings.
There is one here in cost, and I think it's fair to ask this. Is the VELO 3D printing process more expensive than standard 3D printing with supports? And I think you'd have to holistically look at that, right?
You'd have to go back to the entire kind of workflow. So, I mean, it is definitely, in this, printing these areas without supports, you're not, just laying down powder and printing as fast as humanly possible. So basically just dump printing. You are actually taking a little bit more time to do that low angle without supports. But then what you're saving in the full scope of things is, like Aaron talked on, once the outer wall was machined, the abrasive flow or vapor honing, it's a day-to-day process. Once you've vetted through the manufacturing process, you're immediately into that and not worrying about inconsistency of removing supports, as well as even the ability on some impellers or other parts to even be able to remove supports.
Here's one. Has any corrosion testing been done on the Inconel 7810 material? Aaron, maybe that's for you.
For oil and gas, there's been a lot of work in NACE compliance, so adhering at a mechanical level to API 6A CRA. DMP is actually running API 6A CRA powder because of our heritage in the oil and gas industry. But the corrosion testing right now, I think it's a lot of individual places doing it and leading towards a big, more industrial effort, at least from the oil and gas side, to kind of vet that. But from all the papers that have been out there, the things we've seen, it's doable. But I think, again, what we're trying to get at is lowering a lot of these barriers at the upfront allows for those discussions to really kind of take off and not be stuck with, well, how do I make sure the process is controllable? Like one of some of the NACE guidelines want to make sure they have a kind of understanding of the process, having have upper lower bounds. A lot of that information we're tracking can be useful to really help the industries kind of start shifting focus, at least on the Inconel 718 side.
Some question about density of the printed part. What's the density of the printed part? And then I guess after the heat treat, does it change?
So traditionally HIP, so a lot of people do HIP to get to that kind of full 100% density or a little bit closer. Well, we say 99.9% relative density. There are some like on the lower angle processes, and I think we show it on our one of our previous VELOVirtuals. Is having that kind of micro porosity really at the outer layer, and basically being able to close those up through HIP. Whether those matter or not is really where, like Aaron kind of hit on, those are customer endpoint specific. And if you're doing abrasive flow machining or other things, you're likely not concerned with that area. But HIP has just traditionally been done whenever it was well below that 99.9%.
There's a question about other alloys. Aaron, you mentioned the 4 alloys. Are we doing any development, and what does that roadmap look like?
Yep. So we're constantly doing development. A lot of still aimed with the traditional going for production type settings. is traditionally we do material development at our own dime once a machine is released, meaning there's enough demand from an OEM or a CM with enough parts that they want to go do something like an Inconel 7 or the Inconel 316, or sorry, stainless 316 or 17.4 or what have you. It's not that a lot of if it's already a printable alloy, it's not that it's a technical hurdle. All these processes, even though the low angles without supports, like we're confident for some of these that are easily printable will come over. The demand hasn't been there. I think it goes to one of the questions that somebody asked about swapping materials. I think what a lot of folks that are now really pushing towards additive manufacturing are seeing is, if I want to be in production, I do want one printer printing one material. And so a good analogy for energy is if I have 316, 17.4, and 718, do I need to have 3 printers or have my CM have 3 printers, or can I consolidate materials? And what we see typically is that doesn't work all the time. Some customers will not accept a material deviation. But what we have seen is people saying, if I have a 718 printer, or if I can use 718, I know I have a shot of discussing having a 316 or a 17.4 part come in and have an upgrade to a 718. Whereas if I focus on the stainless part, you might not always be, you likely are not going to be able to sub in for a 718 part. And so you're really locked into just being able to print that one stainless part. But like I said, there's no technical challenge in it. It's more of as the demand increases for all the different alloys, kind of solidifying that into the machines that would be running and putting the machine and doing the development.
So kind of got 2 here that we can wrap up with. That I think will be good for the day. You had an impeller. There's a blue ring around it. So there's a question: why is the peripheral surface of the impeller the closed area with the holes? Why did you add that?
When like Aaron was kind of speaking through, going through the actual designing side, the impeller itself, the vanes act as a nice constraint. And again, we're able to print these spans without supports, but this outside area, you're still battling kind of the physics of welding. So this area out here that's completely floating out here and has no good constraint for dimensional accuracy and to just make sure you get the best quality part, we don't even want to deal with that ever being able to peel up. And so we add this wall as a constraint wall to basically hold this completely unconstrained outside section. And so now that I have that wall, I have my vanes, I'm able to cleanly print these low angle surfaces on a part like this.
And as far as the holes, they're just to make powder removal easier. They're not necessary. We can still get them out we get the powder out without them. It just makes our lives easier.
All right. Well, I think we did a pretty good job of getting all the questions. I do want to ask one final one though. What are your closing thoughts? And also, how do people contact you? So those are kind of my 2 follow-ups.
Our closing remarks is, like we kind of had in the conclusion section is, I think everybody's seeing week on week the world is starting to come back, and there is a definite need across all sorts of different product life cycles for additive manufacturing. And for me and Aaron, being traditional design engineers and being able to leverage additive because of what we've done here at VELO and put in place has been pretty exciting. I was just like Aaron, where in the first month I was able to print parts, whereas my previous job I was not able to do so on some of the standard systems. In terms of contacting, I think it's fairly open, whether it's Aaron or myself. At VELO, what we traditionally do is people sourcing a part or wanting to understand the overall process and parts and discuss any of our experiences. Basically having them come through us. That's what we focus on. We focus on the printing side, get a decent understanding on cost, timing, what to look out for in terms of surface finishing and tolerancing. And then once it gets past just the printing side of it and making sure that you're comfortable and understand the design side of it, everything else, after that or before that is really where Aaron and the CMs really come in.
Okay, Aaron, same to you. Closing thoughts, and how can they contact you?
Yeah, as far as getting a hold of us and getting a quote for whether it be impellers or anything else you want to look at for AM, it's duncanmachineproducts.com. Should be an email there to get a hold of us. We look forward to taking a look at your parts and seeing how we can help you.
Okay. Any closing thoughts from the session?
I'm excited to keep doing this. This has been a blast over the past year working with VELO's technology. So
great.
Yeah.
All right. Thanks, guys. Great job today. Great job, Aaron and Zach. And everyone else, thanks for joining us today. Hope you learned a lot. Any questions, feel free to reach out to either one of our speakers.
Yep.
All right, thanks.